A lot of the discourse around large language models is about their unpredictability, and a word that often gets used is randomness. While randomness is an entire complex and interesting area of computer science, use of this word with large language models often more specifically means that the output of these models is unpredictable or unrepeatable, even with the same inputs. This is why people are often surprised to learn that machine learning models are actually deterministic, which means that the same input will always have the same output. Where then does this random behavior come from, and what does it mean for the legal researcher? When we discuss the technical side of machine learning models, we mentioned that not even the engineers and researchers know what the effect of individual parameters in large language learning models do. The reason for this is because of how they're trained. Imagine that you're given an Etch-a-Sketch for the first time and someone tells you that the pointer is currently here, and your goal is to get the pointer over there. You can turn one knob a little bit and see that the cursor goes a little closer, so maybe you turn it the other way and notice it gets a little further away. We know from experience that what you need to do to get the pointer onto the target is to turn both knobs a certain amount and then stop at a given point. Now imagine an Etch-a-Sketch with 15 knobs where each knob changes the output, but not in a discrete Cartesian direction. This would be a much more difficult task, and even manipulating the knobs would be challenging, let alone understanding what each knob does. The Etch-a-Sketch might be mechanically deterministic, but could feel much more random. A language model like ChatGPT-4 is estimated to have roughly 1.8 trillion parameters. Imagine 1.8 trillion knobs that are initialized randomly and need to be tuned so a model overall can have a desired behavior. To do this, machine learning engineers can't manipulate all of these knobs manually. Instead, they use an algorithm called an optimizer. After every adjustment, the optimizer checks the machine learning model's progress and tries to fiddle with the knobs so it can hopefully get itself a little closer. The result is a huge set of internal parameters which determine the output of the model but were not adjusted by human input. This is one way that a kind of randomness can feel baked into the model. Imagine a sentence which begins, "The United States legislative process." The word that comes next could have many correct options. In order to reflect these possibilities, the output of a language model usually isn't a single option but a set of probabilities. Sometimes you only want to select the most probable outcome, but not always. This is where the idea of temperature comes in. Temperature is a setting that increases the chances that a lower probability choice is chosen instead. In language models, this is sometimes correlated with the model's perceived creativity. Since language models work by inputting the previously generated text each time to find the next word, the effect of choosing the path less taken is cumulative. I gave a version of Meta's Llama 3.1 the same prompt and told it to give me the next 50 words. I can specify the temperature as a value higher than 0 up to 1. The higher the number, the more likely it is to select a lower probability output. With the temperature set at 0.0001, I ran the same input 3 times and got the same exact result. However, if I change the temperature to 1, I get 3 results that look very different. Although the output of the model is deterministic, meaning the output of probabilities for each input is always the same, the actual output you end up with can often feel random because temperature allows selection of a lower probability outcome. Another variable that introduces randomness is you, the prompter. In June 2024, a paper called Alice in Wonderland documented how variations in prompts which could look relatively superficial to humans can cause significant differences in the performance of a large language model. An easy way to show this is that when I asked ChatGPT 4.0 how many R's are in the word strawberry, it said 3. But when I asked ChatGPT 4.0 right afterwards how many R's are in the word strawberry, it said 2. Although these queries are functionally the same to the human, the difference to the output was big. Although models are very resource-intensive to develop and train, the way a corporation uses a model can be modified much more easily. This is the case with temperature, but can apply to other parts of the process as well. One such example is a system prompt. A system prompt is a set of instructions which are used to initialize a model. It's often used to specify a role, guide behavior, or provide context. For instance, OpenAI has an example of a system prompt here telling the model what it is, what it should do, and its knowledge cutoff date. Similarly, Lexis is given this prompt. A prompt like this can be easily modified without changing the underlying model and lead to variations in the model's output. In fact, many parameters in a retrieval augmented generation framework can all be changed if a company wants to handle its model differently. While there's little evidence that legal AI tools specifically are doing this, a common way that technology is developed is with A/B testing, where different groups are given different versions of something, so a company can tell which is better. What does this mean for the legal researcher? The overall question that users of this technology are likely to ask is if the information they get from this tool is reliable and consistent. So how consistent can a legal AI with a RAG framework be? I started 2 conversations with Lexis Plus AI asking, what are the elements of arson in the state of Wyoming? And, in Wyoming, what are the points of fact which must be proven to convict someone of arson? This is an intentionally egregious example of a linguistic variation, especially since the term element is a term of art in the taxonomy of law. The divergence between the results was extreme. The overlap between the resources linked in the results was 51%. This surprisingly low number may be due to the number of retrieved sources which were irrelevant. For instance, the second prompt gave me a rule by the Wyoming Department of Family Services that pertains to the requirements for childcare licensing. The rule does mention that a previous conviction for arson disqualifies a potential employee at a childcare facility, but that's the only connection. The difference in the retrieved results and the text of the prompts also greatly influenced the language model's outputs. The first response had a well-organized breakdown of arson into 4 degrees and discussed some elements for each degree. The second response, on the other hand, mentions only 2 degrees of arson and does so twice. This is despite the fact that both results retrieved the relevant portions of the Wyoming annotated statutes, which cover all 4 degrees of arson. The model just chose to discuss and represent them differently. If I were relying only on the second response, I might reasonably be misled to think that there were only 2 degrees of arson since the other 2 were hidden away under view-related materials. But maybe this comparison is too extreme. After all, I am omitting a critical term of art. Let's get a third response and compare. Instead of, what are the elements of arson in the state of Wyoming, I asked, what are the elements for arson for the state of Wyoming? This results in an increase in the overlap between results, but not as much as I expected. Only 86% of the sources from the third response overlap with the first response. The text of the model's answers are superficially almost the same, but have some critical differences, particularly around intent and culpable mental state. The first answer defines first-degree arson as a specific intent crime, but has no other discussion of intent. The third answer lists intentionally, recklessly, or with criminal negligence as the required CMS for third and fourth degree arson and has no other discussion. What about second degree arson? Turns out it also requires specific intent, but if you just had the third answer, you wouldn't know this, and if you just had the first answer, you might be misled to think that the intent requirement for second degree arson was different from first. So which sources of randomness are we dealing with here? I would suspect that the temperature on a legal research tool where accuracy is a priority would be kept as low as possible, especially looking at how close responses 1 and 3 were. Since I ran all of these tests back to back, it's also unlikely that the model handling changed in between these queries. The variable I intentionally manipulated is the prompt, and making those superficial changes led to different activations from randomly configured parameters inside of the model. Language models as a technology are likely always going to have a level of inconsistency in their output. Understanding this can help understand the behavior of language models in all contexts, but especially understanding the reliability of their output for legal research.